all here. So welcome to this first session of the day. We will start right away by a presentation entitled Trapdoor Memory Hard Functions by Benedikt Auerbach, Christoph Günther, and Christoph Pirczak. And Christoph is here on stage, ready to start.
Thank you for the introduction. So as said, we're going to talk about trapdoor memory hard functions. And first of all, let's talk about memory hard functions, or MHFs. So they are motivated by the need for some moderately hard functions in cryptography. For example, password hashing or proofs of work. And so previously, people used computationally hard functions, for example, iterating a hash function 1,000 times. But the issue is that this is not egalitarian. So if someone has specialized hardware, they can evaluate the function much more efficiently. For example, think of ASICs. And now that's where memory hardness comes into play. So now the cost is dominated by the memory usage and not the computational cost. And examples of such functions are, for example, Scrypt or argin2. And there's also drsample, for example, in the literature. And now, when talking about memory hardness, it's important to define how to measure the memory. And here you see the memory usage of an algorithm over time. And we care about the area under the curve. And we call this the cumulative memory complexity, or CMC for short. And now, if you want to look at a memory hard function, the best one to start with is Scrypt. It is the first memory hard function that also introduced the notion. And it's given by a sequential algorithm eval that takes an input w and outputs a value y. And this can be seen as a mode of operation for a hash function h that maps to L-bit outputs. And it also implicitly takes a parameter n, and that controls the memory hardness. In particular, the memory hardness is n squared times L. But this alone does not really prove that it's memory hard, because, for example, someone might come up with a smart way to use parallelism to evaluate it using less memory. But this was ruled out by Alven and others in 2017. They showed that Scrypt is indeed memory hard by showing that every algorithm, even a parallel one, has its cumulative memory complexity bounded by n squared times L in the random oracle model. So now to get some intuition for why this is the case, let's talk about eval. So it takes an input w, and I'll also call it w0. And in the first step of the algorithm, we hash it to get w1. Then we hash again to get w2, and we iterate this hashing until we have n values in total, so up to wn minus 1. So this constitutes the first phase of Scrypt, and then we move on towards the second phase by again hashing. And in the second phase, it's unsurprising, but we're hashing again. But this time we're also including a challenge here in pink. And this pink challenge is one of those values from the top row. And it's chosen in some unpredictable fashion, namely by taking the previous hash function output modulo n. So for example, here, this is the second value. And then in the next step, we do the same thing. Here, the challenge happens to be n minus 1. And this continues again for n steps until we are at the output as n, which is the output y. And now if we want to implement this as honest implementers, one observation is that if we keep this top row in memory at all times, we will be able to answer the challenges on the bottom. And on the bottom we have n challenges, and this gives us roughly this cumulative memory complexity of n squared times L. So now for these functions that this talk is about, trapdoor memory hard functions. So here now what you see are the algorithms that describe a memory hard function, but one that also allows some sampling of public parameters, for example, the hash function. And now we add to that a trapdoor, and also a new algorithm, which we call td-eval. And that takes all the same inputs as eval, and in addition, the trapdoor td. And obviously, we want correctness, so eval and td-eval should agree given the same inputs. And as before, we also want it to be memory hard. Now, here in this case, it needs to be memory hard as long as the trapdoor is not known. Because the whole point of these functions is that if we know the trapdoor, we are more efficient. So that the CMC of TD eval should be significantly lower than the CMC of eval. And why do we want this? One use case is spam prevention. So suppose you have a server and the client, and now the client wants to send an email to the server, but the server demands that there is some memory hard challenge introduced so that the client can send the email. So here the client evaluates a memory hard function, and if we're using a regular memory hard function, then the server needs to recompute it itself, and this is of course expensive. And now using the trapdoor, this can be done in a more efficient manner for the server, which is good because it reduces the resource usage. And there already exists a trapdoor memory hard function. It's called Diodon and was introduced in 2017. And as this session title suggests, it uses ideas from time release cryptography. So setup now samples a hidden order RSA group, where the public parameters are the RSA modulus, and then the trapdoor is the group's order. And now inputs are group elements for simplicity. And the high-level idea is that we take Eurocrypt, which we saw beforehand, but we replace this top row, this repeated hashing, by repeated squaring in this group of unknown order. So this means that the input, this means that the I plus 1 element is now w to the 2 to the I plus 1, modulo n, of course. And if you want to view this pictorially, then here we see Eurocrypt, and in pink we see the changes introduced by Diodon. So the values up top are now w raised to powers of 2, and then each of them is computed via one group operation. And I want to emphasize that the hashes in the second row are still hashes, so they're not group operations. And now if we have the trapdoor, we can skip some of this work. So in particular, in the first step, we immediately compute the last element in the top row, and we can do so efficiently by first performing a modular reduction on the exponent and then performing an exponentiation. And then for every challenge that we get, we do the same thing and compute it on the fly, again using reduction and exponentiation. And now, is this a trapdoor memory hard function? So the correctness is obvious. And for the efficiency, what we see is that eval CMC is the analog of Eurocrypt, so n squared times the size of a group element. And then for TD eval, it's a bit more complicated. And the reason for that is that it kind of takes more time because this reduction and exponentiation are quite expensive operations compared to the ones that eval performs. But since it uses so little memory at every point in time, overall the cumulative memory complexity is still lower. And now for the last question, is it memory hard? And so far this was not known and only conjectured. And this is the gap that we fill in this work by showing that yes, it is memory hard. So our main result is the following theorem, and it states that assuming that factoring is hard, Diodon's cumulative memory complexity is lower bounded by n squared times the size of a group element times 1 over log of little n. And this holds in the parallel random oracle and generic group model. So we do allow parallel queries. And these generic models seem unavoidable since we want memory lower bounds. And this factoring assumption is probably unsurprising to you if you're used to these time release assumptions in generic groups. And now this 1 over log n factor, this makes our proof not tight, because eval has n squared times the size of a group element at its complexity. And we think that this is an artifact of our proof, and it would be great to see if this can be improved in future work. And now to give you some flavor of how we prove this result, I'll give a proof outline in the remainder of this talk. So the high-level idea is that we take the proof by Alvan and others that prove that Eurocrypt is memory hard, and we kind of follow their structure. And it has 2 steps. So the first step is a single challenge time-memory trade-off. And then the second step is kind of takes this and then creates a multi-challenge memory complexity lower bound, which then lower bounds Eurocrypt's complexity. And since Diodon and Eurocrypt are kind of very similar in most ways, we can reuse the second step. And this is great because this is by far the hardest part in their proof. However, we introduce additional algebraic structure in this first row, and this complicates our single challenge time memory trade-off. And so this is the primary hurdle that we solve in our work. And to give you some idea of what this means, let's look at this trade-off by virtue of a toy example. So here you have 6 powers of 2, or w raised to these powers of 2. And now we get a single challenge that we need to answer. So that means we need to return this group element that corresponds to the challenge. For example, here for the challenge 2, we respond with w to the 4. But we could also be adversarial, and our goal is to somehow save on memory. So now what we do is we compute these powers of 2, and then we perform some pre-processing to compress them into a smaller state of m bits. And then we get the challenge after we have computed this state. And to answer this challenge, we are of course allowed to look at our state. And we're also allowed to perform random oracle queries, generic group queries. So this means we can perform some group operations. And then at some point, we need to output the response to the challenge, so w to the 2 to the j. And now, if we want to see a concrete example, suppose we have enough memory to store 2 group elements in full. And an intuitively smart way is to store them in an equidistant fashion. So this means here that we store w and w to the 8. And now we get challenged. For example, again, we get challenged on 2. And now here is why this equidistant strategy seems reasonable. So what we can now do is we don't have this element stored in memory, but we can use the preceding one, so in this case w, and then we recompute the value that we need. So we perform one query to get w squared, and then we again square it to get w to the 4, which we then output. And now what happened here is that we reduced our memory consumption by 2/3, but in the worst case, 1/3 of the challenges require 2 additional queries compared to the honest case. And so this is this time-memory trade-off. We use less memory, but need more time. And intuitively what we just did, so our equidistant strategy, seems to offer quite a good trade-off. And indeed, what we show is that it is close to optimal, so that one cannot do much better. And if we want to see this in a bit of a more formal manner, we get the following statement. So now that we have an m-bit state, which is here in orange, and now for every challenge j, we assign the exact number of queries, so tj, here in pink. And then we get this probabilistic statement. And now if you want to unpack this, what we see is that the probability is over all the challenges j. And since it's greater than a half, or greater and equal to a half, it must hold for at least half of the challenges. And what this inequality within it tells us, so the core idea is that if the memory is small, so if we save a lot of memory, we need to pay a lot of time, a lot of queries to respond to challenges. And if we pick it apart even further, so the left fraction is exactly what one gets if one performs this equidistant strategy that we just saw beforehand. And again, this thing on the right is seemingly an artifact of our proof and is also the reason that kind of makes our bound not tight in the end. And now I'm going to give you a very high-level condensed overview of the proof. And to do so, we do it by contradiction. So now we assume that the adversary answers the challenges quickly. So most of those tj are small. But at the same time, it also uses only a small state of m bits. So this contradicts, again, our intuition from the previous slide. And then we only care about adversaries that can attack a lot of public parameters, so it must hold for most RSA moduli n. And so what we then do in the proof, as a first step, we run the adversary on all the challenges using this small m-bit state. And if you're familiar with the generic group model, you know that you can kind of look at the queries and extract some algebraic representations. And so what we extract here is a system of equations, ax equals b. And intuitively, the solution x to this system corresponds to the discrete logarithms of the group elements that are somehow stored in this m-bit state. So for example, previously in our little toy example, it would be the discrete logarithm of w and then the discrete logarithm times 8. And then in the second step, we proved the following lemma. It kind of states on a high level, if most of the tj are small and the group order is not known to the adversary, so phi of n is hidden, then this vector x has a lot of entries. And this is interesting kind of because we can reduce this to a clean mathematical statement about certain systems of Diophantine equations. And what we need here is some sort of solvability criterion. And what we came up with is one that is slightly loose. So here is the step where we introduce this 1 over log n factor. And now, in the third step, we perform a case distinction. So in reality, it could be the case that this vector x actually only has a few entries. But by the second step, and by our assumption that most of the tj are small, this means that the adversary must know the group's order and consequently can factor n. We assume this to be hard, so this again contradicts our assumption that it works for most RSA moduli n. And then finally, in the fourth step, now we can assume that the vector x has a lot of entries. And since we extracted this vector x by running a on this small m-bit state, we can encode this vector x in m bits. And since this vector has somehow intuitively a lot of info about the generic group oracle, this would mean compressing a part of the generic group oracle, which is impossible by information theory. So this is again a contradiction and concludes our proof. So to conclude, our contribution is that Diodon is indeed memory hard. And open questions are to make this bound tight, so to get rid of this 1 over log n. And other open questions are related to creating other trapdoor memory hard functions. For example, one that saves not only on CMC as a whole, but on memory and time at the same time. Or maybe one for other flavors of memory hard functions, like input-independent ones. If you want to read the full proof and see it in all its gory details, the link is on the slides. Thank you very much for your attention.
Thank you. Is there any question? I have one. So you mentioned a GGM. So which model did you use for GGM?
We use Troop. So our compression argument compresses this random injection in some sense.
So you can use a representation of group elements in memory.
Sorry?
You can use a representation of group elements in memory.
Yeah. So yes, yeah.
Okay.
Thanks.
Is there any other question? If not, so let's thank the speaker again. Thank you very much. Then we proceed to the second speaker. Second speaker will present a talk on time lock puzzles with efficient batch solving. It's by Rachit Garg, Jesko Dujmovic, and Giulio Malavolta. And Rachit is here.
Yeah. Hello. Sorry. Hi, everyone. My name is Rachit Garg, and today I'll be telling you about our work, time lock puzzles with efficient path solving. As mentioned, this is joint work with Jesko Dujmovic and Giulio Malavolta. Let's begin with what are time lock puzzles. Time lock puzzles are a concept which was introduced in '93, where we're basically encrypting or a puzzle of a message M, which takes a lot of time to compute and decrypt. So this puzzle takes time t to decrypt, but it has two essential properties. First, that this puzzle should be efficient to generate. Even though decrypting the puzzle takes time t, to generate this puzzle, it should be efficient, ideally logarithmic in t. The second property is that it should take a lot of time t, even though if you have a very powerful supercomputer which has a lot of parallelism available with it, it should still take sequential time t to decrypt. And the way you can mathematically model this is the circuit that is used to open this puzzle should be at least of depth size t. So this is a cool primitive, and it has a lot of applications. You can encrypt and talk to somebody in the future and ensure nobody in the next few years can ever decrypt your message. But more seriously, there are applications to sealed bid auctions, where you can bid for an art piece until the bidding phase is supposed to open your puzzle. So during the bidding phase, everything is time locked, and during the opening phase, your bid gets revealed. They are used as a building block in a lot of theoretical primitives, such as non-malleable commitments. They're used in blockchains and other settings for minor extractable value prevention. But basically, the idea here is that in a blockchain setting, you can encrypt your puzzle, your transactions, and miners who cannot look at these transactions and arbitrarily promote certain transactions. So it helps against some adversarial corruptions. And the time it is time logged is enough so that the blockchain is already consolidated. And it has more applications in fair contract signing, cryptocurrency payments, and so forth. So amongst these applications, the setting that we are considering in this work is, imagine if there are 3 parties here, and all of them have certain transactions or bids for certain auctions, and they want to, in the end of the protocol, we want to decrypt all the transactions, or get all these messages in the clear, M1, M2, and M3. So to do such a thing, trivially, you would have to solve these time lock puzzles all at once. And the time t computation that it takes to solve one of them, it's a very heavy sequential computation. So to solve all of them, that's a very heavy computation for the auction holder or for the blockchain system as a whole. So if you're scaling this into a blockchain context, there are millions of users, and it really involves a lot of very heavy sequential computation. So, this can also yield attacks, such as denial of service attacks. So imagine if you are doing this auction protocol, and the auctioneer now gets multiple such bids. So each person is now putting a time lock puzzle that's supposed to be encrypted, and the auctioneer now has thousands of these bids, which it's supposed to decrypt. Because this is such heavy sequential computation, it's going to take a while, and it could make the entire system unusable. So this is the goal. The goal is to solve all of these transactions, and this is something which we call batch solving. And in this work, we give an efficient algorithm to do this. So what kind of efficiency are we talking about here? So theoretically, we want to solve all of these puzzles. And the trivial solution, so if it takes time t to solve one solution, and here I'm talking about circuit complexity, so I'm talking about the size of the algorithm that is trying to compute the solution. The trivial solution, if there's n puzzles to be solved, will be n times time t. We call something non-trivial if the time that depends on t is sublinear in n. So the little of n times poly of t, but the time that depends on n can be logarithmic in t. So the more heavy computation is the first part of this expression over there, where things depend on polynomial in t. So that's the complexity that we really want to optimize. And in this work, we show a way that we can compute and open all these time lock puzzles with only solving one puzzle. So the time that depends on t is very, very efficient. So it's not just sublinear in n, it's just solving one puzzle. So this is very desirable. OK, so let me just explain our result. So we give a generic template for converting any linearly homomorphic time lock puzzle to this batchable time lock puzzle, so which can support batch solving. The only prior solution was based on heavy hammers, such as indistinguishability obfuscation, so they were not very practical at all. We also give concrete constructions from different assumptions, such as learning with errors and pairings, and we also implement and give concrete numbers for our protocols. And finally, we also introduce a notion of rogue batch solving. So in this setting where you want to solve multiple of these time lock puzzles, if certain parties are, let's say, malicious and introduce certain bad ways of constructing their own puzzle and cause other parties' output to be incorrectly computed, that is something that we avoid. And I'll talk more about this notion towards the end. Okay. So let's give a roadmap of how our construction looks like. So we'll construct this notion of batchable time lock puzzle, which supports this efficient batch solving. And we'll do it from a relaxation, which I'll call coordinated batch time lock puzzle. And I'll explain that when I get into the construction. But this, we can build the coordinated time lock puzzle, we can build from key homomorphic PRFs and linearly homomorphic time lock puzzles. Also to mention this, we give a generic transformation from a coordinated batch time lock puzzle to a batch time lock puzzle. These linearly homomorphic time lock puzzles are something that you can construct from repeated squaring assumption, and this has been shown in prior work. So what is a repeated squaring assumption? It was mentioned slightly in the previous talk as well. But if you have elements mod n, where n is an RSM modulus, and you're computing repeated squaring operations. So all of these operations are very sequential. So x squared, x to the 4, x to the 8. So you have to do these repeated squaring operations sequentially. And to generate, if you know the RSM modulus, to generate x to the 2 to the t takes much less time t if you know the order of the group. So that is why these are very useful for constructing something such as time lock puzzle. Okay, so then the other ingredient in our list is this key homomorphic PRFs. And this we already knew how to construct from LWE, but in our work we also give more simplified constructions of this. And we also give a constructions from polynomial modulus LW, which was enough for our application. And we use pairings also to construct this new object key homomorphic PRF. For most of the talk, I'll focus on our construction from key homomorphic PRF and linearly homomorphic time lock puzzles to get something which is this coordinated batch time lock puzzle. And then I'll show you the generic transformation where you are in this coordinated setting and how to get to the end goal, which is this batch time lock puzzle. Okay, so this is most of our roadmap. And let me start with the ingredients specifically. So what is a linearly homomorphic time lock puzzle? So it's a time lock puzzle where we have an encryption of M1 and an encryption of M2. And in the end, we want to get an encryption of M1 plus M2. So this procedure should be efficient in time, because the one trivial way to do it is if I take time t, for which my time lock puzzle is locked, I can just decrypt it in time t, and then add them up, and then re-encrypt it. So that's not a solution that we want. These linearly homomorphic time lock puzzles give you an efficient operation, given an encryption of M1 and an encryption of M2, how to compute an encryption of M1 plus M2. So this just takes time polylogarithmic in t. As I've set up this problem, this is already enough to do batch solving. One way to do batch solving is, let's say I have 3 puzzles, M1, M2, and M3. And I want to solve all of them at once. I can use linear homomorphism, and I can compute this output M1 plus M2 to the 2 to the lambda, and M3 to 2 to the 2 lambda. So I'm assuming that M1, M2, and M3 are each lambda bits. So by doing this, I've put relevant information in each lambda blocks. So the first lambda blocks, there is information about M1. The second lambda blocks, there's information about M2. And the third lambda blocks, there's information about M3. So now you can open up the time lock puzzle and get all the 3 at once. So this is nice, but it has a few caveats. One thing is that you have to declare upfront how many puzzles you want to batch. But maybe this is good enough if you know how many people you're attempting to solve together. But the bigger caveat is by doing this, we've increased the size of each individual puzzle. So the size of each individual puzzle now is 3 lambda bits. So this means that the size of each puzzle will grow with the number of parties you're supposed to batch. So in this setting, the size of each puzzle will depend on order n. And if you are doing the n parties and doing n-square communication over the blockchain or any network, that would mean an n-cube communication. So that's really bad. And in our work, we want to avoid this kind of communication overhead. The second ingredient I'm going to use is this notion of a key homomorphic PRF. So a pseudo-random function takes a key k and allows us to evaluate on a point x and gives this output y. A pseudo-random function has this property that if the adversary has access to either the truly random function or a pseudo-random function, they cannot tell the difference between the two worlds. So basically, they're given oracle access, and they can ask for input x and get outputs y. So this is the general pseudo-random function notion. We want a key homomorphic property, which means that if you have an evaluation at a point x on key k1 and an evaluation of a point x at key k2, there's a procedure to compute the evaluation of k1 plus k2 at point x. In our construction, I lied a little bit. It's not just a key homomorphic PRF, it's a key homomorphic punctured PRFs. So what is this notion of puncturing? So you already have this setup and evaluation and key homomorphism property. You also have an algorithm to do key puncturing. So key puncturing basically allows you to puncture at a point x star and compute this punctured key. What does this punctured key do? It can compute any point except point x star. So it allows you to, the evaluation is exactly correct in this setting, and it allows you to compute any point other than x star. So what about the point x star, you ask? That's the security notion. The point, even given this punctured key, the point at x star still looks random. So this is the notion of puncturable PRF, and it's very useful in constructions related to I/O, and it has other applications too. So how do we use these two notions to get the end thing? And our end, the construction is very simple. So here, I'm going to give you a construction of our coordinated batch time lock puzzle. And here, the coordinated means each party has access to this unique index I. So if there are 3 parties which are joining the system, each party is numbered 1, 2, and 3. So they are all having unique indices. Okay, so what do? So I instead put a PRF evaluation of some key ki at point I, because I have this unique index I, and I pad this with my message m. Then what I'll do is I'll output a time lock puzzle of this key k. So I have not done anything useful right now. Initially, I was giving a time lock puzzle for message m. Now I've just moved this to this PRF evaluation, and I'm instead encrypting this key k. So how do I make something useful out of this? Additionally, what I'm also going to give out is I'm going to give out this punctured key at point I. And this is enough to do batch solving. So how do I do this batch solving? So imagine you have this message M1, message M2, and message M3. The message M1 is encoded in this PRF evaluation of K1 at point 1. So I want to recover M1. So through some procedure, I want to evaluate K1 at point 1. So recall that I have these keys, K1, K2, K3, where K1 is the key corresponding to M1, K2 is the key corresponding to M2, and K3 is the key corresponding to M3. What I'll do is I'll use the linearly homomorphic time lock puzzle and compute the encryption or the time lock puzzle of K1 plus K2 plus K3. Once I have this, I'm allowed at least time t once to open this puzzle. So now I have K1 plus K2 plus K3 in the clear. Once I have K1 plus K2 plus K3 in the clear, I can evaluate it at point 1 and subtract it from this equation. But note that there is, even if we have key homomorphism, there is evaluation of K2 at point 1 and evaluation of K3 at point 1, which is still left in the system for me to recover M. So how do I do this? I use basically the punctured keys. So recall that key K2 was punctured at point 2. So using the correct evaluation of the punctured key at a different point, I can actually truly evaluate at point 1. And similarly, K3 I can evaluate at point 1. And so recover the whole thing, or deep-line the whole thing, and in the end get the message. So this is our entire construction. And security is also very straightforward to show, where instead of, we go through a sequence of hybrid, where you remove information about the key and encrypt to something random inside the time lock puzzle, and then you use punctured security to remove information about the message. I won't have time to go over the details, but it follows very straightforwardly. Okay, so let me briefly mention this transformation of a coordinated to batch time lock puzzle. So basically, in this transformation, each party has some unique indices, and let's say in the setting, these unique indices are the slots 1, 2, 3, and 4. And let's say you have 5 users who want to open these time lock puzzles. So here I'm going to sample basically a graph where each of the users is going to sample 2 slots 1 and 3. Similarly, user B samples 3 and 4, C samples 2 and 4, D samples 1 and 2, E samples 3 and 4. Let's say I want to have users B, D, and E come together to solve this time lock puzzle. What I'll do is I'll do a perfect matching algorithm. And in the end, I'll only focus on these particular nodes. And after I perform a perfect matching, I'll be left with a unique assignment. And once I have this unique assignment, I can use my PRF puncturing and all the tricks that I developed previously to compute my time lock puzzle. So this is a generic transformation from any coordinated to uncoordinated scheme. And here we have some formal theorem statements in our paper which give you good guarantees. Finally, towards the end, I want to mention this notion of a rogue puzzle. So what is this rogue puzzle? Imagine there are 3 parties here, M1, M2, and M3. And let's say party M1 is malicious. So what do I mean by malicious? So M1 party is only going to change its own puzzle, and the goal of the M1 party is to have someone, party 2 and party 3, basically decrypt to jumbled information. It could be 100, it could be 1 million, it could be gibberish. So how does party 1 do it? In our current construction, it's possible. So how would it do it? It would change its key ki, which is encrypted under the time lock puzzle, to, let's say, 0. Because it did so, every other party's evaluation would then, once you do the linear homomorphism and you decrypt everybody's output and do the PRF evaluation and do this cross-term cancellation and everything, everyone's output's going to be incorrectly decrypted. So this is undesirable. So in our work, we give a formal notion of what it means to be handling such adversarial attacks. And we also give constructions which prevent such attacks by doing a validity check procedure between what's inside this puzzle and what's inside this punctured key. We also give some evaluation numbers. So just to mention it here, if we were doing 50 million sequential computation, which means like about 5 minutes of computation, the trivial solution would take 15 hours when batching 500 puzzle, but ours just takes 6 minutes. So 5 minutes would be to open one puzzle, and then there's 1 minute for some pairing operations that we do. And also, we are very nice on communication, where if we were using the generic, the trivial solution, it would have been 8 megabytes, but our solution takes 37 megabytes. And the one where there was each puzzle size was growing linearly, that solution would have taken 790 megabytes. So in conclusion, we give a solution for path solving of time lock puzzles, which is good in terms of time efficiency and also good in terms of communication efficiency. We introduce this notion of rogue path solving and give constructions how to avoid such attacks. And we give some concrete implementation and numbers. So thank you.
Thank you. Is there any question for the speaker? Yes.
Hi, thanks for the talk. My question is, do your techniques work to batch puzzles that have different times? So if you come back to the auction bid example, for example, where the parties might want to release their bids at different times, but they should all be open at the same time.
That's a very interesting question. Our techniques do not. I think the first step to constructing that would be a linearly homomorphic time lock puzzle that can handle it. if we get a linearly homomorphic time lock puzzle, I would believe like our techniques can be used. So the first step would be if you have a linearly homomorphic time lock puzzle. Even that is not known in literature right now.
Thank you.
Any other question? Okay, so let's thank Rachit again. So the last talk of the session is entitled Universal Composable Password Authenticated Key Exchange for the Post-Quantum World by Yu Liu, Chengli Liu, and Shuai Han. And Yu is giving a talk.
Thanks for your introduction. Can you hear me? Yeah. Okay. Hello, everyone. I'm Yu Liu from Shanghai Jiao Tong University. Today, I will share our work, Universal Composable Password Authenticated Key Exchange for the Post-Quantum World. This is a joint work with Chengli Liu and Shuai Han. First, I will give the definition of PAC and its UC security. Then I will give our construction of PAC and its security analysis. And finally, I will give a conclusion. So, password authenticated key exchange allows two parties, say a client and a server, to securely establish a session key. The client and server have only possess a low entropy password. The goal of PAC has twofold. One is to make client and server authenticated each other. And the other one is to exchange a pseudo-random session key. So note that the password has low entropy, so the adversary can always try different passwords, invoke the PAC protocol as a client or server using the guessing password to obtain a session key. If the guessing password is correct, then the adversary knows the session key and the security of PAC is broken. So the security requirements of PAC says the above online password guessing attack is the only efficient attack. So in other words, the secure PAC must resist from offline dictionary attack. And now I will briefly recall the Universal Composable Framework for Password Authenticated Key Exchange Protocol. So in the Universal Composable Framework, there are two words, the real world and the ideal world. UC security says for any efficient environment Z, it is hard to distinguish whether Z is in the real world or it's in the ideal world. So in the real world, the environment Z sets the password for each client and server. After receiving the password, the client and server will run the PAC protocol. And the adversary A in the real world plays the role of a public network. It can insert, drop, or modify any message between the client and server. Well, in the ideal world, the client and the server becomes dummy party, and we need to construct a simulator such that the simulator can simulate indistinguishable transcripts of PAC protocol from the real world, and the simulator needs to simulate indistinguishable output session key for each client and server. And here the simulator has no information of password in the ideal world, except with a test password oracle that tells whether a password is the password used in the client or server instance. And simulator can only query the test password oracle once for each client and server instance. So in this paper, we give new generic constructions for UC secure PAC in both random oracle model and quantum random oracle model. And our construction can be based on from LWE assumption or group action Diffie-Hellman assumption, which implies the first UC secure PAC from exogenous. And now I will briefly introduce our construction of PAC and its security analysis. So the basic idea is to make PKE associate with password. And we introduce a labeled public key encryption scheme called LPKE as our fundamental building block. There are 5 algorithms in LPKE. The setup algorithm will output a public parameter PP and a trapdoor TD. The keygen algorithm will take as input a public parameter PP and a label B In the PAC setting, we set the label usually equals to the hash value of password. And the keygen algorithm will output a key pair, PK, and SK. The encryption algorithm will take as input a public parameter, a public key, and a label, and a message. Then it will output a ciphertext C. And the decryption oracle takes as input a public parameter, a secret key, a ciphertext, and it outputs a message M. And here we additionally require an algorithm called check, which takes as input a trapdoor, a public key, and a label. And the check algorithm will output a bit beta, indicates whether B is a label of PK. And there is a natural idea to construct PAC from LPKE scheme. So when the environment inputs the password to the client will invoke the keygen algorithm with a hash value of password as a label, and to generate a key pair PK and SK. Then the client will send PK to the server. After receiving the first message PK, the server will randomly choose a message M, and it will encrypt the message M using the label hpassword. And here we use the encryption algorithm. The randomness of the encryption algorithm is derived from the message M, and this is a similar technique used in Fujisaki-Okamoto transformation. And now, after receiving the ciphertext C, the client will decrypt the ciphertext C to obtain the message M, and it will re-encrypt the message M to check whether the ciphertext C is valid, since the encryption algorithm now is deterministic. And then if the ciphertext C is valid, then the client will compute the authentication token sigma and the session key SK. They are derived by the hash value of the message M and the transcripts. And finally, when the server receiving the authenticated token, it will check whether it is valid and compute the same session key by the message M and the transcript. So to prove the UC security with LPKE of PAC, here are two key points. The first one is what security properties are needed for LPKE, and the second one is how the simulator works. And next, I will show how the simulator works, and along the way, I will point out what security properties are needed for LPKE scheme. So to simulate the first message PK, we require the underlying LPKE scheme has a property called pseudo-randomness of the public key, which means for every label B, the public key generated by the keygen algorithm with label B is indistinguishable from a randomly sampled public key. And with this property, the simulator can just randomly sample a public key and send it to the server. And to simulate the second message C upon receiving public key from the adversary A, the simulator needs to find a way to extract the password from the first message PK. And to ensure there is only one password embedded in PK, we require the underlying LPKE scheme has the property that for every PK, there is at most one password such that each password is a label of PK. And now the simulator can extract the password embedded in PK with the help of random oracle and the trapdoor TD. Same can search all random oracle query hpassword and to check whether hpassword is a label used in PK with the help of trapdoor. And now the simulator can extract the password from PK, and here are two cases. Cases one is the password is correct, which means the password extracted by the simulator is the password used in the server instance. And in this case, SIM can generate the ciphertext C perfectly with password. And if the password is wrong, it means the ciphertext generated by the server uses different label from the label used in public key. So we additionally require the LPKE scheme has the properties that if you use different label from PK to encrypt any message M, then the ciphertext will be statistically indistinguishable from a randomly chosen ciphertext. And now the simulator can just randomly sample a ciphertext C and send it to the client as a second message, in case of the password guess is wrong. And now to simulate the third message sigma upon SIM receiving C from the adversary A. The problem is that the simulator has no SK corresponding to PK. Recall that when the simulator simulates the first message PK, it's just randomly chosen a PK, and it has no information of the password. So in this case, we rely on the technique of FO transformation to extract message M from from the ciphertext C. So the simulator can search all our queries H password and H prime M, and to check whether C equals to the encryption of message M with label H password and randomness H prime M. If there exists such password and M, then SIM can generate sigma perfectly with M and password. And otherwise, SIM can reject the ciphertext C by setting the SK as a failure symbol. Now I will briefly introduce how to upgrade our construction from random Markov model to quantum random Markov model. So we need to first add a CCA secure public key encryption in the second message. And the randomness is also derived from M. And now when simulator receives the second message, C and phi, it can first decrypt phi to obtain password, and then extract message M from the ciphertext C. And now the extraction of M from C becomes a standard Fujisaki-Okamoto transformation technique, and this can also be adapted into the quantum random Markov setting. And here we recall that in our construction, the usage of random Markov can be divided into three functionalities. The right random Markov is used to extract the password from the public key PK. And the blue random Markov is used to the FO transformation to extract the message M from ciphertext C. And the green random Markov serves as a pseudo-random function. And the blue random Markov can be adapted into QROM using the online extractable technique. And the green random Markov can also be proven in QROM using the famous O2H lemma. And the red random Markov seems hard to adapt it into QROM. And the hello idea of our construction is to remove the usage of the red random Markov. We directly use the password as a label of LPKE scheme instead of the hash value of password. And to do so, we must enhance the underlying LPKE scheme such that it can extract the password only with the trapdoor and without the help of random Markov. And we also need to add more security properties to make sure the protocol is secure in QROM. And now I will give a conclusion. So this table shows the time complexity and communication complexity of our protocol, and compared with other PAC schemes from post-quantum assumptions. As you can see, our LWE-based PAC in quantum random Oracle model might be not that practical, but we are the first to achieve this. And our other PAC protocols are practical, even though it is not as efficient as the EKE-based PAC or the AMD-based PAC. And now in this paper, we propose a generic construction for UC secure PAC from LPKE in ROM and QROM. And these constructions admit 4 specific pack schemes with UC security in ROM or QROM based on LW or group action Diffie-Hellman. And it seems I still have some time, so I will introduce how to construct LPKE from LW assumption. So the construction is adapted from the regular encryption scheme, and it's really simple. The trapdoor is the public parameter is a matrix A, and the trapdoor is a matrix T. And with the trapdoor T, one can solve the LW problem. And the keygen is the public key of LPKE is a LW sample and manners the hash value of password. And the SK is also the regular encryption secret key. And to encrypt a message, you just need to plus the label to the PK and run the regular encryption algorithm. And the decryption algorithm is the same to the regular decryption algorithm. And the test now is you can just manage the label to the PK and check whether it is an LW sample. And we see if the public key PK and the ciphertext C contains different labels, then the ciphertext C is encrypted by a uniform public key P, and thus uniform by the leftover hash lemma. And it's also unlikely for 2 random vector V1 and V2 such that V1 minus V2 is close to the lattice. And this is why there is at most 1 password contained in the public key PK. Okay, for more information, you can refer to the full version of our paper. And that's all. Thank you.
Thank you very much. Is there any question for you? Yes.
Okay.
Hi, thanks for the talk. I was wondering whether you could give an idea why the QROM online extraction techniques do not work for the red random oracle.
Okay, so the online extractable technique says you can extract the pre-image M if you get a commitment of the message M. So in our ROM construction here, the ciphertext C, it has 2 ROMs, right? First, it has a hash value of password, and then it has a hash value of the message M. And using these 2 variables, you cannot extract it. So we must to first add a CCA secure to extract the password first, and then use the information of password. We can extract the message M from the ciphertext C. Yeah.
Thank you for the very interesting presentation. Okay. Regarding the common reference string, can you reuse the common reference string over multiple sessions, or do I need a new common reference string for each pair of client and servers?
One for all, yeah. One common reference string for all the sessions.
Okay, yeah. Very useful. Thank you.
Yeah.
Thank you for the talk. For the QROM security, you need CCA secure public key encryption.
Yeah.
So can you do away with that? Can you use like a CPA secure public key encryption instead? Because it feels like you're using the F4 transformation somehow, but you still need a CCA secure.
Yes, we need the underlying LPKE has CPA security.
No, but I'm talking about this for the QROM variant. So you need the PHY, the PKE should be CCA secure, right? So
yes.
Can you like use like a CPA secure public key encryption instead?
No, I think to simulate the protocol, you need the decryption error code in the multi-session setting, I think, since the public key is used for all sessions.
Okay, but if I use a CPA secure public key encryption, then is there an attack, or can you still try to come up with some alternative proof?
I think it may have an attack.
Okay.
Yeah.
Any other question? So let's thank the speaker again. That's it for this session. So now we have a very long coffee break. So please don't forget to come back at 10:45 for the second invited speaker. Thank you.